Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will apply the orthogonality theorem to carry out a hypothesis test in linear regression. Okay, let's go to your lecture notes. So this is the example we're going to be basing our discussion on. Okay? As you can see, we have two goals. Number one, we want to estimate beta 0. And number two, once we have estimated that parameter, we want to carry out the hypothesis test and see whether or not beta 0 is different from 0, statistically speaking. Also, as you can see, we have a few assumptions. We are assuming that we have 3 observations coming from a normal distribution with mean beta 0 and variance sigma square, and we are assuming that y1, y2 and y3 are independent. Okay, now let's talk about the kind of linear model we're dealing with here. So this linear model is equivalent, leads to the kind of assumption or assumptions that we have on the previous slide. Okay, so if yi equals beta 0 plus epsilon, and we assume that epsilon, the random fluctuation, has a normal distribution with mean 0, variance sigma square, then the expected value of yi is just beta 0, right? And the variance of yi would be variance of a constant, 0, and the variance of epsilon I, sigma square. So we have, we have what we assumed on the previous slide. Okay, the assumptions about the distribution of the y's and the distribution of the epsilons are equivalent. Okay. So in this particular case, we have the following in terms of our model and using our linear algebra notation. Okay, we could rewrite the model that we had before like this. So we have, these are the observed responses. First observation, y1 equals 1.1. Second observation of the response, y2 1.4, and y3 equals 1.4 as well. Here we're just factoring out that beta 0, so we have a vector of 1s here plus the vector of random fluctuations of epsilons. Now, since we don't observe the error terms, the epsilons, what we have to do, what we're going to do, is use our assumptions and estimate beta 0, this parameter, using least squares. Okay? Now, you can easily show that beta 0 hat, our estimator of beta 0 in this case, is going to be y bar. Okay? That could be kind of a homework problem. Okay? So again, using least squares and what you guys know, you could easily show that the least squares estimator of beta 0 in this case would be y bar. Okay? Now let me just relate this kind of a new problem to something that you have seen before, an old problem that you have solved before. Okay, so let's go back to the statement of the problem. Now, if instead of using beta 0 here, I used a mu, and I told you, hey guys, we have 3 observations coming from a normal with mean mu and variance sigma square, and I need an estimator of mu, you would go, oh, mu represents the mean, the population mean for a normal. Oh, and you want an estimator for a population mean for a normal distribution? It makes sense that a good choice will be the sample mean, y bar, right? So, what you have done here basically is showing that using the sample mean is a good idea, is a good estimator from a least squares perspective. Make sense? Good, good, good. Okay, so let's go back to that decomposition that we had, right? So we had 3 observations coming from a normal distribution, and we are expressing them as a decomposition of, in this case, 2 vectors, right? We have this guy, 1, 1, 1 times a constant plus something, and this is going to be the residual vector. Okay, this is going to help us estimate the errors, and this guy here, y bar, is an estimate of beta 0. Okay? Okay. Now, let me show you from a graphical perspective what we have. Let's have a graphical interpretation of what we're doing here. Okay? I prepared a few graphs here. So the blue vector, right, represents the vector 1, 1, 1, right, which was that guy we had before in our decomposition, this. So this is basically what we could call the model space, right? So we have the vector 1, 1, 1, and we're looking for a multiple of the vector 1, 1, 1 that is a good approximation for the observed vector of y's. Okay? Okay. Now, by the way, let me remind you that the observations that we have here are 1.1, 1.4, and 1.4. Okay, so going back to our graph, this guy, the black vector, is the observed vector y1, y2, y3, which is, as we said, 1.1, comma 1.4, comma 1.4. Okay, so this is the observed y. Now, this guy here, the dashed blue line, is the model space. Again, note that this is just this dashed line represents all the possible multiples of the vector 1, 1, 1. Okay. Now finally, what we said is that y bar is going to be a good estimator for beta 0, right? So we have beta 0 times 1, 1, 1, and we're going to be estimating beta 0 with y bar. Since y is 1.1, 1.4, and 1.4, if you add them up, that is equal to 3.9 divided by 3, that is 1.3. So y bar, our estimate of beta 0 is going to be 1.3. Okay, so this guy here is the vector 1.3, comma 1.3, comma 1.3, which is the same as y bar times the vector 1, comma 1, comma 1. Okay, so that's from a statistical perspective, right? We found this estimator, right, of beta 0. Okay, but now let's go back to something that we did before. Remember that we talked about orthonormal bases in another video, right? So here's where that discussion will pay off. Okay, that discussion will prove very useful. So now let's talk about this problem using ideas from what we did before when we talked about orthonormal bases. So instead of using W1, the vector, the vector V1 being 1, 1, 1, right? If I normalize that guy 1, 1, 1, right? Clearly the squared norm of 1, 1, 1 would be 1 square plus 1 square plus 1 square, right? So the squared norm of 1, 1, 1 equals 3, right? And then the norm is going to be the square root of 3. So if I divide this vector by its norm, then I end up with u1, which is a normalized version of the vector we started with. Make sense? Okay, and you have seen these guys before, right? Those guys are the orthonormal bases that we talked about in another video. Okay, so anyway, we know that if you're trying to express a vector that lives in R3 using an orthonormal basis, it's going to be very easy to find the weights, the coefficients of that decomposition. All you have to do is find the inner product between your vector y and u1, that gives you the first weight. Inner product between y and u2 gives you the second weight, the second coefficient of that decomposition, and finally the inner product between y and u3 gives you the last coefficient of that decomposition. Okay, so that's what we have here. Okay, we're just finding that weight, that coefficient for that decomposition. Okay, so if y is a vector that lives in R3 in the space, in a three-dimensional space, and the entries are y1, y2, and y3, since u1 is 1 over the square root of 3, comma 1 over the square root of 3, comma 1 over the square root of 3, this is what we end up with. Okay? Now, we are assuming that y1, y2, and y3 are normal, right? So we have a sum of normal random variables. So the distribution of that sum is going to be normal again. Now let's find the expected value and the variance. Okay, we're going to show that for that guy, for the first weight, we have this, that the mean is given by this expression and that the variance is sigma square. Okay, here we go. So at this point what we said is let's use what we know about orthonormal bases to think about this problem from that perspective, and we're going to find that it's going to be useful for carrying out a hypothesis test. Okay, so we're finding this guy. This guy represents the coefficient, the weight, that we're going to be using to multiply u1. Okay, so this is what we found, right? And then if you do that product, w1 times u1, you end up with this. Note that we could factor out that square root of 3, and then square root of 3 times square root of 3, that's 3, right? And this multiplier that we have here is y bar times 1, 1, 1. So I'm just showing you here that our two approaches, right, that least squares estimator matches with what you would end up with using that idea from linear algebra of orthonormal bases. So our estimate of beta 0 would be the same using either approach. But now we also would like to study the statistical properties of that multiplier that we have here, this guy, the W1, sorry. So let's find the expected value of W1, sorry. So it's the expected value of a sum So it's going to be the sum of expected values. So it's this. This is a constant. We could factor it out. 1 over square root of 3, right? And then it would be times expected value of y1 plus expected value of y2 plus expected value of y3. You guys agree? Now it turns out that the expected value of y1, right? Remember that y1 is going to be equal to beta 0 plus epsilon 1. So the expected value of epsilon is 0. So we only have beta 0 here. So we have this times beta 0 plus beta 0 plus beta 0 again. Oops, sorry. And that would be 3 times beta 0 over the square root of 3. So what we end up with is the square root of 3 times beta 0. Right? So, yeah, so W1, that first weight, that first coefficient, it's a linear combination of normals, distribution, normal, expected value, square root of 3 times beta 0. And, you know, we could do something similar for the expected value of I'm sorry, for the variance of W1. It would be just variance of this we know that we could factor out that constant, but we have to square it. In that case, we end up with 1 over 3 times variance of that sum, well, without this guy, right? Oh, let me write it down like this. And what we know is that the variance of a sum of independent random variables is the sum of variances. So that's important. Let's using independence, what we have is that this is going to be the variance of a sum, so 1 over 3 times variance of y1 variance of y2 variance of y3. Variance of y1 is going to be sigma square, right? Because that's a variance of beta 0 plus epsilon 1. Okay, so we have 3 times sigma square divided by 3. That's in the end just sigma square. Okay, makes sense? And just I should say something about notation. If we want to be super careful here, instead of a lowercase, we should have uppercase, because we are talking about a random variable, and we use lowercase for observations. Okay, so let's change this to be careful with the notation. We want to have random variables, not observations here. Okay, it's just a matter of being consistent with the notation. Again, it's just that we use uppercase letters for random variables and lowercase letters for observed values. Anyway, so what we have here is this. The W1 has a normal distribution with that mean and that variance. You can do something similar to show that given our assumptions, W2, that weight, that coefficient, which is given by this, the inner product between y and u2, is this, and then again linear combination of normals, normal, and you can find the mean and the variance of W2. Same thing goes for W3. Okay? Okay. So, now, let me show you the next slide. If we divide it by sigma, right, then the mean is not going to change. Okay? But what's going to change is the variance. Make sense? So basically what you're doing here is kind of you're trying to standardize, right, this guy. Again, give it a shot. Just find the mean and the variance for this new linear combination, if you will, and convince yourselves that you end up with that mean. But now, instead of having a variance of sigma square, you end up with a variance of 1. Okay? Same goes with this, W2 divided by sigma, W3 divided by sigma. Okay? Now, if you recall from either Statistics 256 or Statistics 260, right, if you have a normal 0, 1 and you square it, then you end up with a chi-square with 1 degree of freedom, right? So if H naught, if the null hypothesis is true, and the null hypothesis is that beta 0 is 0, then you have a normal 0, 1 here for the first component. And then if you square it, which is what we have here, right? That's W1. You're dividing that guy by sigma, then you're squaring it, then you have a chi-square with 1 degree of freedom. Same goes for the other two, right? So you have 3 chi-squares with 1 degree of freedom. Now, let me show you something here. W1, W2, and W3 are going to be independent. Why? Using the orthogonality theorem, we know that W1, W2, and W3 are independent. And if they are independent, a function of these guys are going to be independent as well. W1 over sigma squared, W2 over sigma squared, W3 over sigma squared, and if you square them, those functions of those guys are going to be independent as well. Now, from what we did here, right? This guy here in the numerator is a chi-square with 1 degree of freedom. This guy is going to be a chi-square with 1 degree of freedom plus another chi-square with 1 degree of freedom. That's a chi-square with 2 degrees of freedom. Okay? Now, remember that an F distribution is a chi-square divided by its degrees of freedom. So chi-square divided by 1, that's just, the same thing. In this case, we have a chi-square, and we divide it, since we have chi-square with 1 degree of freedom plus chi-square with 1 degree of freedom, we divide by 2, and the ratio between these two quantities is going to be an F distribution with degrees of freedom for the numerator 1 and 2. Okay, makes sense? Okay, so anyway, once you do the math here in this particular case with our observations y1 1.1, y2 1.4, y3 1.4, and x1 is 1, x2 is 1, and x3 is 1, what we end up with is this. Okay? Okay, so now let me say something more about this guy. This is a chi-square with 1 degree of freedom divided by 1. So it's a chi-square with 1 degree of freedom, period, right? You guys remember that the expected value of a chi-square is given by its degrees of freedom, right? So the expected value of the numerator of that quantity is just 1, right? Now, chi-square with 1 degree of freedom plus chi-square with 1 degree of freedom. Okay, we have a chi-square with 2 degrees of freedom. The expected value, 2. Divided by its degrees of freedom, 2 divided by 2, 1. So the ratio, right, under the null hypothesis has this ratio, these guys, the one in the numerator, the one in the denominator, expected values 1 divided by 1 is 1. So under the null hypothesis, the expected value for the whole thing should be close to 1. Okay, so if this quantity is far from 1, what you have is evidence against the null hypothesis, and the null hypothesis is that beta 0 or mu is 0. Okay? Okay, so let me show you how we can do this using R. Okay? Let's launch R. So let's enter our observed y's 1.1, 1.4, 1.4. X, as we said, is just 1, 1, 1. Okay, now let me show you something here. Let's fit a linear model let's use that built-in function lm. Our response variable is y, our predictor is x. Okay, now let's find the coefficients for this model. We know that the estimate of beta 0, right, is going to be 1.3. So note that R goes, hey, yeah, I know that you're estimating just an intercept, a linear model with only an intercept, no slope. So that looks odd, right? So instead of, since R is already understanding that we're doing this, right, to see the results in a better format, let me modify this a little bit. When you do this in R, when you do this -1, what you're telling R is remove the intercept from the model. And you'll see in this case what's going to happen is that, okay, we have only 1.3, because what we're doing there is basically fitting the model like the one we're fitting, with only an intercept. Make sense? Okay, anyway. So what we wanted to do is trying to get something like this using R. Okay? So let's use this new command called anova. Okay? Can you see that this guy 5.07 is here? That's the numerator. That 0.03 is our denominator. The ratio 1.69, well, 169, sorry, it's here, right? And this is the p-value. Okay, note that we said, hey, the probability that you get to see something as huge as 169, given that the null hypothesis is true, is really small, is 0.005, right? So another way of finding that p-value would be like this. It turns out that R has a function to find the areas to the left of distributions. So in this case, the area to the left of an F distribution to the left of 169 with 1 degree of freedom in the numerator and 1 degree of freedom in the denominator, that would be this. But that would be the area to the left. What you want, since it's a p-value, is the probability of seeing something as big as 169 or bigger. So you want the complement, and see that matches with what you have using the ANOVA function. Okay? Anyway, let's recap. Okay? Thanks to the orthogonality theorem, we could derive a hypothesis test for beta 0, a parameter of a particular linear model that we were studying here. The test statistic, right, we have it right here, is the ratio between two chi-square distributions divided by their respective degrees of freedom. Okay, and under the null hypothesis, that quantity, that statistic, we call it, has an F distribution. Okay? Okay, so in the near future we're going to talk a bit more about that ANOVA. Okay? Well, that's it for now. Please take care and keep working hard. See you next time. Bye.